So when you have an error in the lab and you're asked to write errors, if it's a formal lab, we usually do 3, at least 3, and you have to, in a formal lab, list what the error is, what the effects could be, and how you can improvement. Normally when we do, so for example, tomorrow's introductory lab, I'm just going to get you to list 3 and then pick the one that you like the best or you think had the biggest impact on your lab. So tomorrow we are going to do, one of the labs we're going to do is lighting the Bunsen burner and see how the temperature changes. But in an effort to make the lab faster, I'm going to get you to do one position. So the 2 possibilities are 5 centimeters and 7 centimeters above the Bunsen burner. Yeah. And so you'll be assigned either 5 centimeters or 7 centimeters. Then you're going to record your data, and the rest of the class or a different group can take the other position's data, 7 centimeters or 5 centimeters. So in the end, you'll have a complete set of data. But when you do something like that, sometimes people will say, well, Ms. Todd, Billy's starting temperature is not the same as mine. How is that possible? So if you look in this room, there are many sinks that somebody could get tap water from. There's more than one distilled water bottle, which could be influenced differently. If you are starting with something, maybe you're going to hold the thermometer in your hand. Maybe you're generally sort of a hotter person than somebody else. There's all kinds of things that can be introduced. Our job as scientists is to learn how to minimize their effect. And if there is something that you can't minimize, so for example, I'm forcing you to use somebody else's data, then let's analyze it and talk about what we can do to fix it next time. Okay? So when we do labs in this course in grade 12, I never, ever, ever mark your observations for accuracy. If you get something weird that you shouldn't get, part of your job will be to write either good analysis questions, sometimes it's right in the question, or to write good errors. Okay, so let's do that. Okay, so this one, I realize this should be systematic, sorry. I like these bullseye pictures because it helps to explain what the difference between systematic error and random error is. So Mr. Devine definitely talks about the difference between these two things. And he even said sometimes, there are things that science teachers can do to sort of introduce error to get you to think about what's going on. So something that is systematic can be very frustrating for students because you can't really tell necessarily what's going on. So if your errors are all really, if your values, your measurements are all really close together, then you think your data is good, right? Often a question is, how does your data, what's the range? And a cluster of repeatable experiments, that's like the hallmark of science. But what happens if you are starting with something that already has a problem? So your measurements may be precise or close together. So here's a little cluster of measurements close together, but they are not close to the bullseye. They are not accurate. So unlike grade 9 and 10, where you mostly just did controlled experiments, we are going to do experiments where you're going to calculate percent error and see how far you are from the known value. So we don't usually use measuring tapes, but maybe in physics you do. If you use a measuring tape that is not metal and it's kind of a plasticky material and it's already stretched out, then every single measurement you make, yes, you are using that stretched out material, but it's introducing error for every single measurement you take. A scale that always reads too high or low. So if your scale has been calibrated incorrectly, and that's why nobody shares my scales with me, we get to keep them in here, because when you move the scale around, then it can affect how it reads. And if it always reads too high or too low, then your values will be far from the bullseye or the center. And then if you're reading the values at an incorrect angle. So let's say you're going to do a graduated cylinder. You're supposed to do the bottom of the meniscus. Yes, you could have the same person reading the volume measurements, say standing there looking at it over top. Yes, they are doing the same thing every time. The data looks the same, but really they're not reading it from the correct spot. So this can be harder for a student to recognize. And sometimes it can be in the moment hard to fix. So last semester I did a lab with my grade 12 students, and they tried to get a neutral solution, which was green. And so they got the green, and then they used the machines, the LabQuest, and measured the pH, and it was coming up to be 2. And they were like, Ms. Todd, this doesn't make sense. And in that moment, there was nothing I could do about it. They had just completed the neutralization. So I said, okay, just write it down. And then that can be one of your errors. That's a systematic error. Obviously, the machine is not calibrated correctly. Versus random errors, where the values are all over the place, but they are a little bit closer to the known value. So this might be, usually there's at least 2 people in a lab group or 3. Maybe you have to time something. I do a couple of the readings, then Ben says, now I want to do them. And then Caitlin says, now I want to do them. Yes, we are using the same equipment. We're doing essentially the same procedure, but a different person is reading when to start, when to stop. Then that can be a little bit more random. Rounding values up or down. So depending on what kind of science you take, like say you want to be an engineer and you're going to build a bridge or a building that's going to support people, then we often talk a lot about significant digits, uncertain and certain values. That rounding it's shocking how quickly the rounding, when you're doing multiple steps in a calculation, how quickly it can affect your final value. So scientists, the further you go and the more intense your measurements are, then you'll probably focus more on how certain am I in this measurement, and then your calculator doesn't know what you're doing. You have to think about what kind of number should I write down, okay? Oh, it's spelled wrong here. Actually, I'm going to fix this. Sorry, you have to fix this. You don't have to put capitals, but that bugs me. Sorry. So systematic error has the same value for every measurement. So it looks like it's good, it's reproducible, but but then the accuracy has been decreased. It is possible to reduce this type of error, including making sure things are calibrated correctly before you start. And one of the ways we're also going to do this is percent error, or compare it to a standard. So when you have a lab, so say you're going to use our scales. When you turn the scale on, it actually counts down for you. It says 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And it might even say the word test. And what it's doing is warming up. Sometimes if it's fluctuating after a while, so this morning I did some measurements and it was all good. And then all of a sudden the last digit started to flicker. It was like, 99.355, 356, 357. It started to really change. So if that starts to happen, maybe I turned it off and turned it back on. You have to recalibrate. checking the equipment. Are you using equipment that is old? Are the calibrations rubbed off? In grade 9 and 10, we often have graduated cylinders that it's almost impossible to read the calibrations, those like beige ones that are all plastic. If you noticed, we don't have any of those because the calibrations, it's like impossible to see. I bought for my house a measuring cup from the dollar store, and then I was washing it, and the red calibrations actually wiped off. So obviously I was like, oh, I guess I can't use this anymore. So we don't use stuff like that even here. And certainly, again, if you get more and more intense and further along in your education, hopefully your equipment is better. Is the measuring tape stretched? Are you starting knowing that this is no good? Random errors is unpredictable, which can be very annoying. So one of the things that we can do is use more data. So when we do something like titration with that burette, that was $92. It's got really good calibrations. We're going to do 3 trials and take an average. So that is a common thing to do. Often we do 3 trials of things, take an average value, and even to the point where maybe in grade 11 and 12, if one of the trials has data that's like an outlier, you would ignore it and even do 4. So the more data sets you take, then the errors are hopefully reduced. So this is one of the unfortunate things with having the internet and social media as a news source. You can't report, or you shouldn't report data on a sample that is really small. Like in this classroom, if I said who had pizza for lunch and there's 30 of you, 25 of you put your hand up, that's 80% of the class. I can't then say, 80% of St. John's eats pizza at lunch. Why? Because I took a small sample. That's not how data should be reported. Okay? So this is a big one for us. Our scales are a little bit sensitive. So when you use the scale, this one's not so bad. There's only one counter, but that one over there, the one on my left, has like the big long lab bench. Just take a look down the lab bench and see if somebody is moving the scale or hitting the counter. Then it can actually affect the reading. Usually it'll be the last digit. Some students will just ignore that last digit, and that works too. This is hard, drafts in the air circulation. So you can see we have sort of 2, maybe even an intake 1. Oh, I see 4. So we have lots of air vents back there, which is great for air circulation. We like that. But it will even affect, you'll notice some people in the middle bench, when you try to light the Bunsen burner, it'll be all over the place. So it can be tricky. And obviously, you and I can't fix this. So a little bit more random. This is hard for when you were in grade 10 and you did lasers. So the strength of the light or dark in the room. We're going to fix this, right? This one we can fix. We are going to use graduated cylinders to measure volumes instead of beakers. And when you do something that is not as quantitative, so that's really what we're trying to move towards, then you're going to automatically be less accurate. If you're, stretch the elastic, well, how far? So it's better to say stretch it 4 centimeters, then everybody can do that 4 centimeters and keep it the same. This one's a big one too. People take turns taking readings. So try to use the same person. Somebody is the watcher of the thermometer. If you change the water sample, take it from the same bottle or the same sink so you're not introducing random errors that you can fix. Okay, so systematic errors are worse because you think things are going well, but if the instrument was broken, you might not even know. Then random errors can be reduced by average measurements, which is a really common thing for us to do. And we will do this all the time as well. We're going to check with a standard or known value. Or something we do, it costs us hundreds of dollars to get our scales calibrated so that if I'm telling you it has 3 decimal places and that's pretty accurate, I want to make sure that that's true. So when you are writing errors, please, 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 please do not write a couple of things on here. Now, errors should really be the best part of your lab, okay? So I encourage students when we do a lab, think about things that could happen or did happen to you. Maybe the people beside you had something really bad happen, and you can use that as one of your errors. And you don't need to feel bad that you jotted down, the people beside me didn't measure correctly or whatever. That's okay. The things that you shouldn't do, you shouldn't write human error because that's just really broad. What about human error? What happened in your lab? And so identify a specific mistake or problem. And you really shouldn't write Billy is a bad lab partner. Billy spilled the solution. Try to keep it away from names as well, okay? So here's an example. Billy and Sally are working on an experiment where they are trying to measure how long it takes a toy car to travel down a ramp. Billy is supposed to be starting the timer when Sally says, now. He is distracted by students in the hallway, and Sally notices that he hasn't started the timer and says, start it now. So Billy should not write in her lab report, Billy did not start the timer on time. So instead, and you don't need to be long-winded. It does not need to be this enormous run-on sentence. You can be very concise. Timing the distance traveled was inconsistent. Precision in times recorded was affected by inconsistent start times. Nothing in here says Billy was distracted by students. Okay, so it kept it within the ideas of what the lab is. What are we measuring? Timing the distance traveled. Was it consistent? No. Okay. So again, most of our labs, and sometimes it is just systematic. There's just nothing we can do. We do our best. We don't have enough gas jets, or, I don't want to run out of time, so we have to collect class data, whatever. So if something like this, though, there are situations where you have a lab idea, and there are things that you can do to minimize the errors when you do measurements. So a group of 3 students that has been assigned to measure the growth of the plant height for a week using a ruler. So right away, one of the things that we're going to try not to do anymore is qualitative. So if you're like, did your plant grow? Oh yeah, I see it grew. What? How much, right? That automatically introduces error. So doing quantitative measurements, that helps. But then things like this, you have to kind of think about when you're thinking about the lab. On Monday and Tuesday, Bennett measures and the height increases. These are my kids, just so you know. Bennett measures and the height increases. On Wednesday, Max measures and the height decreases. Then on Thursday and Friday, Chloe measures and the height increases. So first of all, this is really vague on purpose, right? Let's say this was a quiz question. I would want you to be able to write a million errors. But if you have 3 different people measuring the height, does it say anywhere that they use the same ruler? No. So that could even be a possible error. And if you don't want to be like, if you're worried about, should I say like, this is what happened for sure, or maybe you're making suggestions about what could have happened, you could even write height measurements may not have been taken using the same ruler. That's okay. You sort of, this is maybe something we would do, using a ruler might be something we would do in chemistry. In biology, which obviously we're not going to grow plants in here, but if you have, you can think about yourself and how you feel in the morning versus the afternoon versus the evening. It doesn't really say when they measured it, so that could affect the height as well. One of the things you can really sort of always do, whether you're doing physics and you're measuring speed or time or distance, height, how long a reaction takes, any of that kind of stuff. Tomorrow we're going to do temperature. Then what you really want to consider too is you always start a graph or a representation of data, and usually you take an initial value or your start value. So you can think about when you take measurements, how does my start value compare? If it's a different person, are they starting at the same soil level? You don't really know. Did Bennett push it down farther? Did Chloe rest it on the soil? You don't really know. So when you take measurements, think about what the start value looks like. So for example, tomorrow, when you have different groups value for this, maybe their starting temperature is not the same as yours. That could be because they use different water. So then when you have that kind of error, when you have a different start value, then again, every single error is affected by, or every single value is affected by that start value. So that is something that you can use commonly as a common error. I'm going to put initial, not start. Yes. And then sometimes what students will say, Ms. Todd, I don't even know what an error is that I could write. So even something like this, even when I write this down, the initial value may be the initial value may be different based on where the ruler was placed in the soil. Some of you who are into biology and into plants will say, well, wouldn't the soil value even change because it uses the soil? Yes, right? So there's all kinds of things that can stem from one idea. So the more specific you are, then the greater variety of errors you can write. So for example, if I just wrote here, the measurements were inconsistent, the measurements of what, right? The measurements of time, or the time that the measurements were taken, the height measurements, where it was placed in the soil. So the broader you are, then that sort of limits how many errors you can write. So even though you don't need to be long-winded, your errors do not need to be 5 sentences long. The more specific you are, then probably you can get more ideas from one type of error, okay? And again, I don't need you to be fancy. I don't need you to be like, oh, the precision here is influenced by blah, blah, blah. You can be You do not need to talk like a fancy scientist. You just really have to consider what is happening. What did I do? Okay? Okay, I'm going to go to, let's talk about this for a second first, and then we'll go do the examples. More examples. Okay, so, I just said that. Be careful of writing ambiguous errors. If you can ask how or why, then it's probably in your advantage to answer the how and the why, because then you can probably get more than one error, okay? Writing errors that are the same. So if you say a really common thing we do is acids and bases, right? So if you say we estimated the volume of hydrochloric acid using the meniscus, and we estimated the volume of sodium hydroxide using the meniscus, those are the same thing, okay? When you write an error analysis, it could be things that happened or things that could happen. Take a look at the procedure. And sometimes when you read it through, you're like, this is what? This could be this. Am I, should I think of it this way? Those could be errors. And again, you can kind of take a look at what somebody has happened to somebody else and jot that down. And you don't need to say to them, oh, you idiot, look what you did. Just use it as your error, okay? Please never ever, let's make a highlight box around this. Never, ever, never, never are we going to say using the wrong numbers in our calculations, that's not an acceptable error, okay? Because this has nothing to do with what you did in the lab. They have to really be part of the lab. You don't need to label them procedural or observational. You don't need to label them systematic or random. They just need to be part of what could happen in the lab. So sometimes, usually, even in grade 12, you're just going to list errors. Tomorrow, I'm going to get you to just pick one of them to state how it affects your lab and how it could be improved. But then when you do the formal lab, you would have to do it more formally. Remember, we want errors to be easy marks, okay? Usually people lose marks and errors because they write this, or they only do 2 instead of 3. And unfortunately, then I can't even give you part marks, right? So being on time will be important. I will always give you a heads up. Hey, watch out for this. And then even as I'm talking, if I say there are common lab errors, jot it down, okay? And that can be one of your errors. Even though errors is often the last question or the last thing on a worksheet, some students like to do that first, because then later on, you might forget what you did, you forget what, the people beside you did, or whatever. And the more you're involved in the lab, then the more opportunity you have to think of things that you can fix or that went wrong. So I recommend 2s or 3s. And it's not because I'm mean and nasty. It's because that's the best for you, that you will get the most out of the lab. When you get to 4 people or 5 people, then there's too many people standing around, and that's just boring. And then you don't get to actually do the lab. And then trying to do the work later is harder for you to do. Okay? All right, so let's do some more examples. And this is so in the safety review worksheet, there is a question sort of like this, a scenario, write some errors, and there is many that you could write, okay? And again, you don't need to be fancy, you don't need to be long-winded, you can be concise. So the first one, the triple beam balance, if you remember, and maybe even grade 9 teachers are like, you know what, we're not going to do that anymore, because the triple beam balance itself, that's where you move the thing across and it moves the weight and measures it. Or if you ever go to the doctor's office, Sometimes, or in the weight room, do they still have it where you like weigh yourself with a like an old school, not digital thing? You stand on it. Do they still have it? Yeah. So right away, I don't use triple beam balances because they're so inaccurate, but or they're you're automatically estimating the value but with your eyes, but that's okay. We won't worry about that. So it says we didn't use the triple beam balance right. So yes, that is a very good error. That is something that definitely could influence your results, but you can write this in two different ways that potentially you could actually count as two different types of errors. Okay, so 2 marks versus writing something like this. That's so ambiguous that it doesn't get you the marks. So when you use the triple beam balance, let me see, in case you never got to use one. This is exactly what ours look like. They're beige like this, and you put your sample on here, and you have to move these across and make it line up here. So there's a like an arrowhead here, and you have to make this line up with that arrowhead. So you're essentially trying to make a numerical measurement, but qualitatively figuring it out. That doesn't make any sense. Why would you do that? Let's use digital, right? Okay, so you could write something about how it was difficult to line up the arrows to make sure you could read the mass. Or actually, you know what? I'm going to be fancy. Sometimes when you're in a doctor's office or the weight room, sometimes they use the like a triple beam balance kind of idea because using a digital scale to weigh yourself can really be influenced by where you put it. Is there something under the scale? It is a little bit more accurate for mass, but you really have to know how to use it. So you could even write something like, our results became more accurate or our results became more reliable when we learned how to use the equipment or when we practiced using the equipment. So again, then taking an average of the values can be a way to help minimize that error. So that could be something you could write as an improvement. I hope this isn't true in weightlifting class, but in weightlifting class, if you have to take measurements of yourself over the semester, then maybe, and someone's helping you, maybe you would want to use the same helper every time. You could write something like that. So there's plenty of things that you could write instead of just being really super ambiguous. Like, I mean, I hope your teacher wouldn't give you a hard time if your weight went up a little bit or down, but Hopefully there's no marks assigned for that. So this one I included because this is what we're going to do tomorrow. So if you have, let's say you have a pot that is being heated on the stove top. So the heat is right in the bottom. And we choose materials that will conduct the heat, and water itself will conduct heat. But if you were going to measure the temperature of the pot of water, where would the hottest part be? Right, the bottom. So if you measure at the bottom always, then you're automatically making your temperature hotter than potentially it should be. So some people will then in the procedure say the thermometer should be held at a consistent height. You could say that. You could just talk about this, that our temperature readings were taken closest to the heat source, so our start value could have been influenced, right? So again, you can even go back and think of, is my error systematic? Did I automatically start with crappy data? Okay. So I'll write about the bottom of the beaker, but you can write, it should be at a consistent height or whatever. Actually. That's not how you spell closest, sorry. To be honest, we usually say in chemistry, we say initial value, not start value. That's usually more for physics, but it's the same thing. But again, there is plenty that you could write here. If you're like, I don't like that error, I want to write something else, please do. Oh, goodness. Sorry, my spelling is atrocious. So wrong measurement. So right there of what? What? So this again really limits what you can write because there's plenty of things that you can do. Often we do more than one type of measurement. We'll do temperature and mass. So you could get 2 errors out of that. So really the less ambiguous, the more specific you are, then the better you will, you'll have more opportunities to write errors. So you can, I don't know, we're going to measure, well, we already did a temperature one. So we're going to do volume tomorrow. So let's do volume. So what I'll do is, now hopefully in grade 11, we're not going to do this anymore, but maybe someone, if you ever help in a grade 10 class or grade 9 class or something, and they have to write errors, their teacher might not emphasize the importance of a graduated cylinder, but let's say you used a beaker to measure volume. Then you could say the wrong equipment was used to measure volume. The beaker used to measure volume had 5% error in its calibrations. And right there, that's introducing error in your measurements. So it's tempting. I even want to write a graduated cylinder should be used, but that's the improvement, right? So you can write that, of course you can, but you could even just stop here if you just have to list them, okay? Okay, so this one says high and low temperature values were weird. So what can happen, our thermometers aren't perfect. So as I said, ours do not have mercury. Technically, mercury would work better, but it's toxic, right? So for obvious reasons, we don't have them. So what can happen is if you start to get close to 100, so most of the labs we do will say, don't let your water boil, because when you get close to 100, then what happens is you'll see it's usually red. The red material actually starts to separate. So inside the thermometer, it'll be like solid, and then all of a sudden it'll be like this. And then it's like, okay, where do I read the measurements? How do I do that? So what you can write, and you can't fix that, I can't fix that unless we get mercury thermometers, which we're not going to because they're toxic. So you can say even something like, you can write high and low values. When you're at the edge of the range, that can be called the extremes, are the data is unreliable or unusable even because of equipment limitations. There's nothing you can do about it. So as I said, lots of times the lab will say right in it, don't let the water boil, don't let it get close to 100. And so really, if you're doing something like this, you can have similar errors in different labs. That's okay too. If you're using a water bath and having to measure the temperature, then this definitely, our thermometers, they limit how accurate our values are for sure.